Okay, we're starting. We're of course going to continue with partial fractions. By the way, in light of the snow day, I'm not sure how we're going to make the class up, but in terms of the quiz, I'll probably just let you guys do 2 quizzes on Wednesday. Because the quiz that I'd have at the end of this section will be short anyway, because you really only have one topic on it, partial fractions. So I'll just give you back-to-back quizzes. One big party session. Partial fractions. Continued. So we know that technique to break up larger fractions into smaller ones. The technique, we went through most of the steps. There's really one last step. So 1, if the degree of the numerator is greater than or equal to the degree of the denominator, then perform. So this was the first step, to make sure you have the right form for this method to work. So you perform long division or synthetic division. Or otherwise simplify algebraically. That was the first step. The second step was to factor the denominator fully. The third step was to create smaller fractions using the factor denominator. Stair denominators. With certain stipulations. 1, you would put on those denominators a generic numerator. So you'd have a generic numerator with arbitrary constants. This generic numerator must make sure that the numerator must be 1 degree less than the denominator. Second of all, for repeated factors, that is, factors in the denominator that have multiplicity, count up to the power. The fourth step is what we didn't get to, is solve for the arbitrary constants. Using 1. I'm going to give you 2 methods to be able to solve for these constants. Using 1 and you can actually mix and match them of 2 methods. That will be the final step. Once you find the arbitrary constants, you will know exactly what the specific fractions are that went into creating the bigger fraction. So this is the method of partial fraction decomp in summary. Let's make sure that we kind of remember the essentials. What if I had something like 3 over x How would I break that up? What is the partial fraction decomposition of that fraction? Oh, you guys are still copying this stuff. I'll wait until you guys copy.
Could you factor x squared minus 4 to get down to?
Okay, so there is a key word in one of these steps. It says factor denominator fully. So if you see some parts of the denominator that can be factored further, you'd actually break that down. So I would again go further here. So it would be x plus 1 squared times x minus 2 times x plus 2. Sure. Now, so now the denominator is fully factored. And of course we mean factor over the rationals. Technically you can factor x cubed minus 7, but you'll get like radicals in there and non-polynomial powers. Well, you'll all have polynomials. It'll be nasty. Okay, so now what? How do you break that up? What would the pieces be? Are you guys still copying? What would the pieces be? How would I break up this fraction?
A over x.
Okay, so start with a over x.
Plus bx. B over x plus 1 squared. But you put plus, oh, so we're breaking apart that now? That x plus 1.
It's a repeated factor.
Oh.
So you count up to the power. Remember we did that last time where if it was like a cube, you do the denominator, then the denominator squared, then the denominator cube. That's what I meant by count up to the power. Or count up to how many times it's repeated. We did that. So here's x plus 1. The factor we're looking at is x plus 1, which is a first degree polynomial, which means the top needs to be a 0 degree polynomial. So the top is still just a constant, but you still count up to the power. And if this were a cubed, I'd have a third one that says d over x plus 1 cubed. How do we continue?
So plus d over x plus 2, plus e over x plus 2, and then plus fx plus, oh wait, is it fx squared plus gx plus h over x cubed minus 7.
Right? You always have to remember that the numerator needs to be 1 degree less than the denominator. Therefore, if the denominator here is an x cubed, the numerator needs to be a quadratic. Yeah.
Is x cubed minus 7? Isn't that also factorable?
Yeah, I mentioned that, but it's like you'd have radicals and unnice things in there. Yeah.
What do you do for 3?
What? 3?
That 3 in the numerator. You had 3 over all of it.
Oh yeah.
No, the goal would be you would want to solve for the arbitrary factors so that when you combine all this, it ends up being a 3. Right, so the 3 is something you know ahead of time. The 3 is there. But this is the first step in actually figuring out what are all the little smaller fractions that went into creating this bigger fraction. We're now in step 3, where we broke it down with a bunch of arbitrary constants. The goal would be to solve for these constants so that if I plug in all the constants here and actually combine these little fractions, I would end up with this huge fraction where the numerator is 3. That's going to be the goal. And there are a couple ways we can do that, a couple standard ways. I'm going to show you about them. I'll also show you a little trick that deals with in one scenario. But yeah, there usually will be two methods, two main methods here. So now, we would want to, in general, no, we're not going to do it for this one, solve for the arbitrary constants so that combining these small fractions gives us the original. Yes, Nicholas?
So for the last factor there, the fx squared plus g of x plus gx plus h, is that because the numerator is 1 degree less, so you have to have it like,
Yeah.
have all the
So
factors?
if the denominator is a cubic, I would put a quadratic on top.
Okay.
And if the denominator had the fourth power, then I'd put a generic cubic on top.
Okay, alright. Thanks.
So that's kind of where we got up to last time, being able to break down a fraction in this way. Now let's go a little bit further. I'm not going to go further with this one because this example would take us forever to find all these constants. Because these methods tend to end up with like a system of equations to solve or something similar. So now let's look at finding those arbitrary constants. I'm going to describe to you method 1 for finding these. Both methods kind of start out the same way, but how you execute the last part is going to be different. So here's method 1. Multiply both sides of the equation by the denominator on the left, plug in convenient values of x. Convenient just means you're going to plug in values of x that allows you to kill most of the arbitrary constants, and then you solve for the remaining ones. Right? So you're just reducing the complexity of the equations. Because you will obtain an equation that has to hold in order for these fractions to add up to the other one, and so you just know that it should work for all these x values. So let's do an example of that. Example. Let's say I wanted to, what was my example? X squared minus 5x plus 6. So this is the thing. 1 over x squared minus 5x plus 6. Find the partial fractions of that fraction. X minus 5x plus 6. Okay. So you're given this. Now you might be given an integral in front of this and you want to integrate that. And one option you might have is using partial fractions. So let's actually do that here. So what would be the first step in these partial fractions here? One, check that the power on the top is less than the power on the bottom, which is true here. Next step. Yeah?
Factor.
Fully factor the denominator. So we end up with this guy. Can we factor that?
Yeah.
What's that? Minus 3 and minus 2? Okay. And now let's break that up. So this is x minus 3 times x minus 2. What would that break up as?
A over x minus 2 plus b over x minus 2.
Okay. So now, that we've already covered so far. Now we want to figure out what does a and b have to be in order for these two guys to add up to this fraction. what I'm going to do is I'm going to multiply both sides by the denominator on the left. Right, so I'm going to multiply both sides by, you know, x minus 3, x minus 2, and multiply this whole side by x minus 3, x minus 2. This is going to kill all my fractions. So now that would mean that 1 is equal to a times x minus 2 plus b times x minus 3. And so now we can apply the second step of this method. Plug in convenient values for x that will allow us to solve for a and b. So what would be 1? So this equation has to hold for these two fractions to combine to that fraction. So it means this expression needs to hold for every value of x. Give me a convenient value of x you want to plug into this. Yeah?
0.
You could plug in 0. It'll hold for every x, but there's convenience is paramount here. You don't want to waste a lot of time here. 2 would be a nice value. Why would 2 be a nice value? Because I plug in 2, it kills the a, but it doesn't kill the b term. So I would literally have an equation with one unknown. That's pretty easy. So x equals 2 is a convenient term for me here. Because now plugging in x equals 2, I would end up with 1 is equal to b times 2 minus 3. Which would now, that's just an equation with one unknown. That's trivial to solve. So that's just b times minus 1, so you end up with your b must be equal to minus 1. You can do the same thing again. What is another convenient x value to plug in? 3. 3 allows me to kill the b, but leave the a alive. I've already solved for the b, so now I can get rid of him, so I can plug in 3. And so what would happen is I would get 1 is equal to a times 3 minus 2, and the b would die. So that would tell me that my a needs to be 1. Which means this means that the expression 1 over x squared minus 5x plus 6 can be written as a over x minus 3, but my a is 1, and b over x minus 2, but my b is minus 1. I found the partial fractions. Now this guy, before this technique, and if you wanted to integrate this guy, that would be pretty annoying because you'd have to sort of like complete the square in the denominator and do like a trig sub or something like that. You'd have x minus 5 over 2 squared plus like some fraction. It'd be really annoying. But writing this as that way, that's easy to deal with. That's actually pretty easy to integrate. So there's going to be ln of x minus 3 in absolute values minus ln of x minus 2 in absolute values plus c. Right? You can just look at it and see the answer. Right? So being able to write this in smaller chunks is a very powerful technique. And this is one way to do it. Right? Write your fraction, break it into the pieces, multiply both sides by the denominator, you will get an expression that needs to work in order for that statement to be true. Plug in convenient values of x that eliminates a bunch of terms and leaves a fewer terms for you to solve for. If it's possible to plug in a term that eliminates everyone except one guy, that's good. Sometimes it's not possible. You'll get an equation with 2 unknowns, and then you get another equation with 2 unknowns, and then you do like simultaneous equation. Right? That's kind of the worst case scenario. But at the end of the day, we can eventually break this guy down into that. This means, by the way, this is not a part of the example, but just so that we can relate this back to what's important to us, integration is very important to us in Calc 2. So this means if you had this guy, you could just realize that that's this guy. I don't know if this is going to show up. And this is really easy to integrate. Whereas before we learned about partial fractions, your way of integrating this for partial fractions probably the best thing to do here would have been to do something like complete the square in the denominator, so this would be x minus 5 over 2 squared. And on the outside, that would be 6 minus 25 over 4. So this guy would simplify to the 1 over x minus 5 over 2 squared plus 1 over 4. And then you do something like x equals, you do something like x minus 5 over 2 is equal to 1 over 2 tangent theta. And that's just the beginning of your problems. Right now you're going to plug that into this, get a trig function that you have to solve. Then you're going to have to write a triangle to back substitute everything. It will be hell, right? Whereas you kind of go through this method. And by the way, this one sort of lends itself to a shortcut. I'm going to give you a shortcut where if you factor the denominator, if you only have linear non-repeating factors, there's even a quicker way to get to the answer. You can almost do it in your head. Other situations are more complicated, but this is one method. Right? So let me show you another method. So this is method 1. Right? The main part in method 1 that makes method 1 is how we go about the second step. Method 2 is going to have the same first step. Okay? So the idea that you can plug in convenient values to eliminate some values, and so you can solve for the other ones. That's one way you can go about it. Any questions on this? So let's do method 2. Kind of starts out the same, multiply both sides by the biggest denominator, so you get a sort of nice equation. But here's how you go about the second step. You combine like powers of x and then equate coefficients. This will give you a system of equations to solve. It'll be linear equations by the time you get to this level. So it'll be a system of linear equations to solve for the arbitrary constants. So let's actually go through that method with this same example so you can kind of compare and contrast. You might like one method more than the other one, and that's completely fine. You can always do it one way. I find method 1 is easier when it actually applies. It's easier to just solve for one thing at a time. But ultimately, we should get to the same answer. So here's how that would look. So you're given this. First thing you do is check that the powers work out. The degree of the numerator needs to be less than the degree of the denominator. Check. That works out here. If that didn't happen, I would do long division or something to break it down. Next step is to fully factor your denominator. In that case, we did this. Next step is to take your fraction and break it up into pieces where each factor in the denominator gets to be a new denominator over here, according to the stipulation that we've made before. Right? So we would eventually get to this step. Now here's how we continue. So we multiply both sides by this. So this would again give us 1 is equal to a times x minus 2 plus b times x minus 3. So now here's how this step works. You would combine like powers of x, which means on the right side what you're going to do is you're going to start expanding everything. And you're going to combine like powers. So let's group all the x's to the first power. There are 2 such terms. So this is just a plus b x's. Now let's group all the x's to the 0th power. Those are just the constants. and now you equate coefficients. This is an important technique. We'll use this later on when we're doing series and things like that. Sometimes this technique comes up. But realize what you have here is that on this side you have 0 x's and 1 as the constant. Whereas on this side you have a plus b x's and this as the constant. Now in order for these sides to be equal, the number of x's on one side need to be equal to the number of x's on the other side. Which kind of means, this is where what equate coefficients mean. The coefficient of x on this side must be equal to the coefficient of x on that side. So that means that a plus b must be equal to 0. The constant term on this side must be equal to the constant term on that side. So that means that minus 2a minus 3b must be equal to 1. So now I obtain two equations. This means that my a plus b must be equal to 0. And my minus 2a minus 3b must be equal to 1. So I end up with a system of equations. Two equations, two unknowns. And so now I just solve that system. How do we solve this system? How do you go about solving that system?
Solve for one variable, then plug in for the other.
There are a couple ways. You can do the elimination method or the substitution method, which you were doing. So one thing you could have done was multiply equation 1 by 2. And then add them. Right? So here you get minus b equals 1, and so you end up with b equals minus 1. And then you just plug them in. You know that now that a plus minus 1 must be equal to 0. So this means that your a equals 1. You could also do, so this is the elimination method. Like, I don't particularly care what method you use, just make sure you do the right thing. Or you can do the substitution method, which is what Olivia just mentioned, is where, like in equation 1, you can solve for a, you get minus b in equation 1, plug into equation 2. So this means in equation 2, I'm just going to replace the a with minus b. And so that would give me 2b minus 3b equals 1. So you have minus b equals 1. So again, b equals minus 1, which would mean that your a, which is minus b, so your a would be positive 1. Right, so there are a bunch of ways you can get to that, but you solve that system that results, and therefore that implies that this guy breaks up into this guy. And whatever consequences would follow from that. Okay, so those are the two main methods. And you can you can even mix and match them. You might get an expression where you use the convenient values method to eliminate some variables and solve for others, but you still end up with an expression where it's just easy to just set up some simultaneous equations even after doing that. But these are the two main ways to approach it. Here's one nice way. So now this is an application of a class that's above this class. So if you guys, some of you are math majors and you do a class called complex analysis, you'll eventually go over a theorem that's called the Residue Theorem. It has a very specific application to finding partial fractions. In general, the formula is a little bit more complicated, and I don't think it's worth it for you in Cal 2 to know it. But in the case where your denominator is just linear, non-repeating factors, the application of the theorem is very easy. So here's a trick. If denominator is a product of linear, non-repeating, so you can't have a multiplicity higher than 1 factors, which this guy clearly qualifies. Okay. So if you have something like this guy here, right? You could actually skip all this work and actually do it mostly in your head. It's an application of the residue theorem. So you know that this would break up into a over x minus 3 plus b over x minus 2. This is. So here's how it would do for each factor. Figure out what makes denominator 0. And then you're going to plug that x value in here. Ignore the 0 part of the denominator. You do this for each, do this for each fraction. So here's how that would actually apply. What makes the denominator here 0? X equals 3. Go over here, cover up x equals 3, plug in 3. What would we get? 1 over 1. So 1 is the numerator of that guy. What would make this 0? 2. Cover that part up, plug in 2. You would get 1 over negative 1. So the answer to that is negative 1. That's the answer. And you can actually keep this going, right? So you could have something like 1 over x minus 2 times x minus 1 times x plus 3. You know that you'd have to split this into a over x minus 2 plus b over x minus 1 plus c over x plus 3. But we can just apply this theorem. X equals 2 makes that 0. Cover that up, plug in 2. Right? You would end up with what here? That would just be 1. This would be 5. So it ends up being 1/5. That's going to be your a value. 1 makes this 0, so cover that up and plug in 1. That would be a negative 1. That would be 4. So it's minus 1/4. X equals minus 3 makes that 0. Cover that up, plug in x equals minus 3. That would give us a minus 5 times a minus 4. So that would just be plus 1/20. That's your answer. It only works for linear non-repeating factors because the formula depends on the power of the factor. So whatever the power r is, you'd have to take the nth derivative of the total fraction. So if this was like, oh, to the 5th, you have to actually take the 5th derivative of using the quotient rule, and it gets complicated going higher. But for linear factors, it's pretty easy to plug. Yeah.
Sorry, there was no rule or anything like what the a's, that the arbitrary constant had to add up to what was originally the numerator, right?
No, the arbitrary constants on the tops do not have to add up to 1. But the fractions as a whole, if I have this fraction and that fraction, it should add up to that fraction.
Okay, sorry.
But that's just a shortcut. You can actually get through shorter. So you factor and you see something like that, breaking it to this part is easy, which is all the more reason to avoid trig sub and do partial fractions. The theorem in its generality gets more complicated if your factors are repeated or if the factors inside here are not linear. And so I don't think it would be worth it. But for linear factors, it's great. Okay. So here are the examples we're going to do. Do we skip 6.4 in our syllabus? So you know everything you need to know about partial fractions. That's the whole method. But let's just go through some examples. Something like just write out the examples, so if you guys want to practice some of them while at home, you can. How do you go about integrating something like that? How do you go about integrating something like this? I think, notice this example is an example that we did using trig substitution. So I kind of want you to use partial fractions here. And you can compare and contrast the answers. Like, what method would you prefer? What's in your plus 3x minus 4 dx. Homework here is due Wednesday. Next Wednesday, whatever date that is. I believe our next topic would be, do we skip 6.4? 7.4. So approximate integration and improper integrals. So we have 2 more topics to the next test. So let's see. We'll probably spend part of Tuesday finishing this up, or maybe all of Tuesday finishing this up. Approximate integration is also one class, so I probably finish that on Wednesday, and then improper integrals will happen Friday. So that would mean, and hand waving here, just kind of approximating things a little bit. By next week, Friday, we should have everything complete for the second test. So we should complete that on the 16th. When is spring break?
Last day of class is the 21st.
Last day of class is the 21st, yeah, Wednesday.
The 21st?
Yeah.
Okay, so the second test is right as we come back from spring break.
That Wednesday or Tuesday?
When do we come back from spring break?
We come back to
The first Wednesday after spring break.
Okay.
So you're
Um,
gonna
so-
make us be that person like crying in the corner?
Yeah. Yeah, so to my best well, I'm pretty sure that'll be it.
Yeah.
So
Is that a good thing?
test 2, first Wednesday after spring break.
Fourth.
I have it.
Okay, probably take 5 minutes to get through one of these guys. That guy looks like he's going to be quite annoying, but we don't have to integrate it. We just need to find the partial fractions. But with all these examples, you'll kind of get a feel for what method you prefer, or whether you like to mix and match methods, because you'll encounter a lot of different scenarios by solving all of these problems. So you'll know, okay, in this case there really isn't a convenient value that's going to kill everyone except one term, and so I might want to do something else. It's just for you to get used to you being able to solve. There's no wrong way here. There's no real recommendation about what to do, I would say. It's all a matter of what are you better at. If you're super good at solving simultaneous equations, or a system of equations, I'd always do method 2. But if you prefer to not do that, or you're good at something else, I would probably do method 1. So it's more of a personal choice here. I don't really have, there's no real recommendation for never do method 2 in this case. There's no such thing. Okay, so how would we start here? Always start the same way. Make sure that the highest degree in the numerator is smaller than the highest degree in the denominator. That's great here. So now what? Factor the denominator. So this is just going to be 5x squared plus 20x plus 6 over, what's the factor?
Plot an x first.
Plot an x, you'll get x squared plus 2x plus 1.
And
You can factor that. This is x squared plus 20x plus 6 over x times, that'll just be x plus 1 all squared, right? How would you break that up?
A over x,
So it's a over x plus
b over x.
b over x plus 1
Plus C over X plus
plus c over x plus 1 squared. The next step would be to multiply both sides by this denominator, so we end up with 5x squared plus 20x plus 6 equals, this would be a times, the x's would cancel, so this would be x plus 1 squared, plus b times, one of the x plus 1's will cancel, so this is b times x plus 1. And then you would have plus c times x. There are convenient numbers here, so I would probably apply method 1. You might want to expand out and just get simultaneous equations right away, but I would prefer to actually plug in some convenient values. Because notice that if I can plug in -1, that would kill these two and leave my c. If I plug in 0, that will kill these two and leave my a. And then I can solve for those two guys, and then literally plug in any other random number, and I can solve for the guy that's left over. So I would start by saying x equals -1. What would that mean? This would give me 5 minus 20 plus 6. That would go, and I would end up with minus c. What's 5 minus 20 plus 6? Minus 15 plus 6, which is what, minus 9? So here my c is positive 9. Then I plug in another useful number, like x equals 0. That would give me 6 on this side, that would kill this, and that will leave me just with a. So I get a equals 6 right away. So I know c, I know a, I just need to find b, so I'll just plug in any other random number. Probably plug in a number that's really easy to work with, so something small, so maybe like x equals 1. That would leave me with 5 plus 20 plus 6 Here I would have 4a, because I plug in 1, and that's 1 plus 1 squared. Here I would have 2b, and here I would just have c. But the thing is, I know what a and c are. So that would mean, so what would that give me? That's 25 plus 6, that's 31. A is 6, so this becomes 24 plus 2b plus c is 9. And now I can solve that for b. What would that end up being? 24 plus 9 is 33. Subtract 33, that's minus 2. So I get 2b equals minus 2, so then I end up with my b equals minus 1. And I found the partial fractions. So this means 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x is equal to a over x, but my a is 6, so that's 6 over x. B over x plus 1, my b is minus 1. And c over x plus 1 squared, but my c is 9. That's the partial fractions. And it wasn't asked here, but you can imagine if I needed to integrate this, it'll be the same as integrating each of those, which is not so bad. So dabble with those other examples, try to get a feel for the method you like. I'm partial to method 1, as you can probably tell, just like plug in stuff and kill everybody. And then, but there are cases where you can't kill everybody. Like if this was like an x squared plus 1, then there's no way I could kill everything. So we'll stop there. So I have a double quiz on Wednesday, so the quiz will be on what I wanted to quiz you on this week, which is trig substitution and partial and integration by parts. And then I'll also do the remaining quiz on partial fractions.